Okay, so before we start today, a couple of things to go through and announcements. So homework 2 will be, or has just been posted, so you'll be able to access that. So I do want to talk about that a little bit before we start. So this homework is going to be a little bit different than homeworks you guys have done before. So last class we talked about sort of risk preferences, and we're actually going to have this sort of interesting homework that will elicit your own risk preference. So the way this works is the second homework is going to be multiple choice, but you don't select an answer, you assign a probability that you assign a probability for each of the choices, and the probability will correspond to a certain type of score. So let's say you have A, B, C, D, and you're not sure what the answer is, so you just give a identical probability for each of these, so 0.25, 0.25, like this. So if you plug that into here, you'll see that at 0.25, that's 0 points. So this would be 0 points. Let's say if the correct answer was C. And if you were to instead do something like this, 0, 0, 1, 0, well, you get the correct answer here, so you get the maximum number of points, which is 5 on the chart. But I'm going to warn everyone right now, do not, this homework will be curved. Do not do this, because if you get the wrong answer, you automatically fail the entire homework. So if I put 0 here, you'll notice that my score is based off of this calculation. The log of 0 is -infinity. And so we are sort of building into the assignment this risk of a risk that is associated with your grade. And so depending on how risk averse you are, then you could weight these guys a little bit more equally. So you know, if you are slightly more confident, maybe you'll do something like 0.9, 0.033, something like this. If you're more sort of risk averse, you might set this at a lower one and set these guys a little bit higher. So not only do you have to sort of figure out what you think is the right answer, you also need to come up with a sort of strategy about how much confidence you want to assign to any particular answer. Again, I will reiterate, do not put zeros. Some people have tried that and have not been successful sometimes. Some of the questions are going to be ambiguous, and that's sort of on purpose here. Okay, any questions about this homework? Don't wait till the last day to do this. It will not turn out well.
So how many questions are there?
Let's see, how many questions are there? There are 15 questions. Actually, there's kind of like 12. You get a couple free ones at the end.
each one of those has the same kind of ranking strategy?
Yep, exactly.
Okay.
And you do still have to show your work for all of this when you turn in your assignment, but yeah, just put a sort of probability score next to each of the choices. Okay. The other sort of assignments is that we need to start thinking about final course projects. So projects can be done in teams of up to 2 people if folks want to partner up. And we're just going to start with a project proposal. So this is just a short, like 1-page description of your project by February 8th. Please make sure to either meet me online or email me to discuss whether the sort of project that you're thinking about doing makes sense before you submit your first project description. I can provide some general tips and guidance. So please make sure to reach out before that. Any questions about this first start of the course project?
Yeah, I have a question.
Sure.
I was looking at the course project guidelines before, and then it says the due date for project proposal is March 5th. So we should just scrap that and then follow the February 8th as the new deadline.
Yeah, I need to update that. I realized that that's kind of like the wrong timeline. So we'll start with this one.
Okay.
Yep.
Thank you.
I'll make an announcement just so everyone has the same information. Okay. So today we'll be talking about sensitivity and uncertainty analysis. So the first plot here is a plot of the life cycle emissions in terms of CO2 per megajoule for conventional gas and unconventional gas. So we talked a little bit about these 2 fuel sources. Okay, so I'd like to have a quick chat with someone want to volunteer to help me interpret this graph? Anyone? Just raise your hand.
I'll volunteer.
Okay, sweet. Okay, so what would you say about the life cycle emissions comparison between these 2 fuel sources?
Based on this chart?
Yes, just based on this chart.
That conventional gas is quote unquote better for the environment and releases less emissions.
Yeah, great. Okay, and how about now?
Well, that error bar is pretty large.
Okay.
But I would, I'm not sure.
Yeah, does this change your interpretation at all?
I would like to see the error bar for conventional gas too. But yeah, because if this is at, the lower end of this large error bar, it has the potential to release a lot less emissions.
Sure. So you have less confidence that the unconventional gas is better, or sorry, is necessarily worse than conventional gas.
Yes.
Yeah. Okay. How about now?
Well, now I'm really not confident that conventional gas is better.
Okay. And that's because the range kind of blows up a lot higher, possibly, right?
Yeah.
Would that answer change now?
Now I would say that conventional gas is
Yeah. So that's exactly right. So this may seem like super obvious to everybody. Okay, we see these error bars, and I think it provides this sort of additional interpretation. But I think that's something that folks should always be sort of on the lookout for. And when you look at other research, when you are doing your own research, it's important to sort of provide as much information as possible, and that it's also important to realize the way that people interpret some of these results. If you fail to incorporate sensitivity or uncertainty, it can push forward like a different sort of narrative, right? We can see the interpretation of our plots are going to change quite a lot, depending on whether or not you include this sort of extra information about uncertainty. And if you don't include it, if it's something without sort of any of these bars, I think you're oftentimes it's like you're implying that there isn't any sort of uncertainty. I actually chose this particular example because I was actually at a conference where some like VP of Chevron was showing this chart about LCA emissions for conventional gas versus unconventional gas. And the figure looked really familiar. And actually it turned out that the figure was doctored from a paper that a colleague of mine had published, and they had removed the uncertainty bars. And the sort of implication in this person's talk was that, oh, this thing is definitely, cleaner than this other source, but it's a lot less clear once you include some of the uncertainty bars. So kind of a lesson to keep in mind. The topic that we're talking today is a crucial one for being able to provide the correct interpretation of results when you do your research or when you're looking at other people's research. Okay, so uncertainty. What is this? The lack of certainty, a state of having limited knowledge where it's impossible to exactly describe its existing state or future outcomes. Okay, so if it's something that we don't know, how can we go about quantifying it? So what we were going to talk about today is this idea that even if you don't know something, sort of knowing that you don't know it is an important concept to apply into your analysis. There's this sort of famous quote by Donald Rumsfeld way back in the 90s. So there are known knowns, which are things that we can say that we have good information about, that we know about. There are known unknowns where we know there are things that we're uncertain about, but maybe we have some perspective about what it is that we don't know about. And then there are things that are unknown unknowns, And those are kind of the hardest to capture. And we'll think about how each of these concepts can be applied rigorously in a quantitative setting. So we're going to try and break this down systematically, looking at sensitivity or scenario analyses, also kind of known as sort of what if analysis. So this is thinking about computing the effect of changes in individual inputs on a model prediction. This is kind of the simplest approach to incorporating uncertainty and sensitivity analysis into modeling. Oftentimes, this is very useful to help break down the individual contributions of components of your model to a particular outcome, and allows you to do kind of these simplified single unit analyses. Uncertainty propagation, calculating the uncertainty in the model outputs induced by input uncertainty. And that's going to be closely related to uncertainty analysis, where we want to compare comparing importance of multiple input uncertainties in terms of their relative contributions. And so these will tend to be a little bit more complex than the sort of scenario and what if analyses, because they seek to incorporate all of the uncertainty that we kind of know about into our model. Okay, so the first one that we'll talk about is known as one-way sensitivity analysis. And tornado diagrams are a useful way of being able to display this analysis. So one-way sensitivity, essentially you make a graph that varies a single variable from a low to high end range. And so the nice thing about the tornado diagram is it can show sort of many one-way plots on a single chart. And oftentimes the way it's arranged, it kind of looks like a tornado, where you have the sort of largest one on top going to the smallest contribution at the bottom. So that quickly gives you kind of a rank order of the sort of most impactful parameter down to the sort of least impactful parameter. So let's show a practical example of this. Consider some kind of function y equals f of x1 and x2. So x1 and x2 are inputs into the model. And the whole question is basically, okay, as I change x1, or if I change x2, you know, what happens to my y? One example that we can look at is from last class. We have this Pennzoil court case. So just as a sort of quick refresher, there is this decision tree that we made. And you can sort of accept or reject the initial counteroffer. And then if you reject it, right, there might be some probability of this new counteroffer, a probability that you go to court, and then some probability that they'll reject the counteroffer that you're making, in which case you can accept a new counteroffer or you can go to court, right? And so there were some questions last time about, oh, how do we know that, you know, a particular probability is going to be, you know, at whatever value that we set it at? Or how do we know that, you know, a particular counteroffer or if the court award is going to be set at whatever those values were. So we can try and essentially mess with these values and see how the outcomes may actually shift if you change the payouts, or if you change some of the probabilities. So let's take a look first at changing the payouts. So this is an example of a tornado diagram where I can change the payouts. And essentially what I'm doing here is in this case, it's kind of a simplistic thing where I'm just changing the value of that final outcome by plus or minus 50%. So right in the middle is the value that would be, is where the value would be the same. And you can see, I can really easily see how the width of the bar kind of tells me if I change values of particular outcomes, which ones will have the sort of biggest effect on your final value. And so these are the probabilities associated, or sorry, the outcome values associated with accepting the Texaco offer or accepting the Texaco counter offer. It kind of makes sense actually if I go back, right? So that's these guys. These are the two values that aren't really affected by other these are values that aren't affected by other probabilities. Oh, okay, so I see a question. Did I make these in an app or program? So I made these in R, which is, you know, a statistical programming software. But you can actually use an Excel add-on. I would recommend when I was first doing this, we would use this program called At Risk. I'll just type it in, and I can provide a link to it during the break today in chat. I think you can only use like a trial version right now, but if folks are interested in it, we might be able to get a license for the class if a lot of people want to use that. You can build it in Excel sort of manually, but it's kind of a hassle. Okay. So basically, the kind of point here is that, okay, it's an easy thing to do where I could vary things plus or minus 50%, and I can quickly identify which factors kind of get influenced the most in your sort of decision-making process. The kind of interesting thing about this particular problem is that you can do a two-way sensitivity analysis. So this is kind of trying to do the same thing, except you affect multiple sort of variables at once. And so I can show a two-dimensional plot of what happens when I alter two particular variables. So in this case, I'm going to look at, okay, what if the payout from the court is different, and what if the sort of counter offer is different? You could go and do like a three-way sensitivity or a four-way sensitivity of multiple variables. However, the visualization of those outcomes becomes really kind of hard to see. And so let's take a look here. Oh, hang on one sec. Okay, two-way sensitivity. If I change the sort of award from sort of winning big, and I change the award for the second counter offer, we can see how the expected value of your decision tree sort of starts to change. And you can see, right, these sort of numbers here. And in the context of this particular problem, it can actually help to shift the decision. Okay, should I accept the counteroffer or decline the counteroffer in sort of both of those decision nodes. So in this case, we can see it can create these sensitivity maps that provide essentially a map of the strategy for whether or not you would accept or decline the first offer and the second offer. So we can see over large ranges of the sort of core award and the counter offer that you should, whether or not you should sort of decline or accept the first offer here, and then in the second one, whether or not you should accept or decline. And so you can see how varying by creating these sensitivity maps, it gives us a sort of method of sort of dynamically addressing changes in the outcomes for any uncertainties that we may have sort of less confidence about. If we think back to that decision tree and this sort of fundamental question of like, oh, I don't actually know all of this, all of the information about how much money I would get paid if it went to court, or how much the like second counter offer would be. And one of the things you can do is by creating these sort of maps, you can say, well, okay, look, like I can see that across like values that I think might be reasonable for what like a court might award, or for what the second counter offer would be, most of the time my decision should stay the same, right? Like there's kind of one sort of dominant decision, and that can help your sort of decision-making process, instead of just relying on, hey, if this value were this and this value were this, now I can see over the whole range of values, hey, like it still makes sense for me to choose, one strategy most of the time. Or, your decision might look a lot closer, something like this, where, you can see maybe it's closer to like 40-60 or something like that. And again, you still have more information to work with here, where you might say, yeah, so if I were just looking at a static value, my decision would be this, but I can see that the outcome might be more sort of closely split. And so having done the sensitivity analysis, we're helping to improve and inform our decision-making process. And so you can see why this might be useful for stakeholders to do this kind of analysis and provide more confidence in choosing a particular decision. Okay, I see a question. What is a court reward? So this is in reference to the example, right, from last class in this decision tree. So yeah, just a quick refresher, right? One side is suing another side and they're deciding whether or not to go to court. The court award is basically if the offer goes to court, or if the lawsuit ends up going to court, you could end up winning a large amount of money. And so this is just displaying what would happen if that amount of money changes. Okay, I see another question. Go ahead.
Yeah, it's Amrita here. So this appears to be something like a heat map kind of output, which we see out here. Yeah. So here we are changing for the first diagram, we are changing which parameter, and for the second one, we are changing which one. That if you could elaborate that a little.
Yeah. This is for the first decision node, and this is for the second decision node. Sorry, I should probably label this better. So I should say, in regards to two-way sensitivities, usually you would see some kind of heat map like this. Because our problem here is all about whether we say yes or no, it transforms the outcome into kind of a binary outcome of accept the counteroffer, reject the counteroffer, or accept the counteroffer, reject the second counteroffer. So in this case, in the first plot, this is about whether or not you would accept or decline the first offer, and this is about whether you would accept or decline the second offer. And the teal is basically saying you should decline the first offer, and the red here is saying you should accept the first counteroffer, and this is applying to the second. Accept the second counteroffer, decline the second offer. If you remember, the expected value of this branch here was a lot higher than taking this. And so the only scenarios where you would accept the first counteroffer is if your payouts in this whole branch of your tree are a lot lower. And we can see that's reflected here, right? You can see that, oh, how low would the combination of those two things have to be to say no to the counteroffer? It's in this kind of range of values here.
Okay.
Yeah.
Thank you.
Yep. Any other questions about this? Okay, we can do the same thing looking at that insurance example, which was the final example from last class. So this was the whole thing about whether or not you should buy insurance or not buy insurance, right? We have, if you buy insurance, then your expected value is 2,000 minus what you pay for insurance. If you don't buy insurance, there's some 90% probability that you just get your $2,000 payout, but then there's some probability that, you know, the disaster happens and you lose $800 in value out of this. And then we have this utility function to represent sort of the risk preference of the individual. So what would happen if we looked at, if we changed the type of people who were making the decision, maybe from someone who's risk averse to risk neutral to risk seeking? And then how does the rate of the insurance change? And what happens to the profit of the insurer? So we can do things like modify the damages and the probability of those damages. We could modify sort of the parameters of the utility function. And we can see what happens here. Okay, this is actually not the best kind of diagram for a tornado chart. This should be kind of on, these two should be on the bottom so that you're kind of having the largest bar at the top. But you can see that if I were to vary each of the parameters by say 50%, then you can see how the value changes for your insurance payout break even and for the insurance company's profit. So same type of thing here. We're just doing a simple sort of one-way sensitivity to look at the sort of change in the range of values that you would get in each of your outcomes. And this is a sort of quick and dirty way of being able to identify which parameters kind of make the sort of biggest difference if you're varying them by some set amount. Another common way to do this is instead of doing it like plus or minus 50%, say you have some idea of the reasonable sort of range of values that you would alter any particular input by. Doing this kind of analysis by that range of values tells you how your outcome can change in comparison across all of the one-way uncertainties in your input. I didn't make a sort of chart about this, but another sort of common way of doing the sensitivity analysis is using something called a spider diagram, which is actually the exact same thing in principle. It's just the display of your output is a little bit different. Okay. The next thing we're going to talk about is moving into sort of more complex territories of uncertainty analysis. So if you have more information about the uncertainty for a particular value, let's say instead of doing this sort of range, you had a distribution for the sort of values for your input. So in contrast, right, to what we were just talking about, where we were just looking at sort of like a low to a high end range for an input, suppose you have information that says, oh, okay, I actually know that it's more likely that these sort of values for my input are to occur. In other words, we have some idea of what the distribution of your input values might look like. You're starting to get a little bit more complicated, right? Because you can't just vary them from the, as we're doing in the sensitivity, because that only gives you sort of the range of possible outcomes, but it doesn't give you the likelihood of possible outcomes. So what we want to do, the sort of concept here is that this sort of iterative assembly function in the middle, that's just kind of your model, right? And you're taking, you want to be able to take distributions of inputs and get, instead of one set output, you get a distribution of outputs. So this, one of the techniques to do this is known as a Monte Carlo. So Monte Carlo is a statistical sampling technique. So this was sort of famously well developed like a century ago, working on sort of the Manhattan Project in the 1940s. There's this method for doing many iterations of picking inputs to sort of generate a distribution of answers. take a look. So the way this works is that I, one, specify probability distributions for uncertainty variables. So you need to have some sense of how likely it is that a particular input value could take, or input variable could take a specific value. What I'll say in the real world is that, you know, oftentimes if you don't have any information about what those values are going to be, you could kind of do the same thing as what we were doing before, where you pick a low to a high, and then you would just have a uniform distribution. Oftentimes it's common to have some kind of like normal distribution. So you have some, you know, information about parameters of your input value based on some mean value and a standard deviation, or the other sort of common one is what's known as a triangular distribution. We'll see an example of this, where you have a good idea of the most likely value, and then a low and a high, and then your distribution kind of looks like a triangle. And in this case, you know, you have a little bit more information than just kind of a uniform distribution. Okay, so the way this works is that you're going to randomly sample values from your input distribution, and then you run through your entire model calculation, and you do this sort of again and again until you end up getting sort of many answers, and those many answers will construct an output distribution. So importantly, like a Monte Carlo analysis doesn't produce a quote unquote right answer, it produces a distribution of results that you then have to sort of interpret. Okay, any questions about this? So the classic example of a Monte Carlo is actually being able to use this technique to calculate pi. So let's say you're on you're stranded on an island by yourself, and you need some way to pass the time, and you want to be able to calculate the value of pi accurately. One way you could do this is you can draw a circle and transcribe that within a square in the sand, and then you could just grab some coconuts or rocks or something and huck it into the square. And so what you want to do is you want to sort of uniformly scatter points inside of the square. If you then count the number of points inside the circle versus the total number of points inside the square, you can use a relationship between the area of the square and the area of pi to calculate the value of pi. And you can see in this equation here how you would do that. So area of squares, length times width, let's say that's length 1. Area of circles, pi r squared. So it would be the radius is 1/2. So then the area of the circle is pi over 4. And therefore, the area in the circle is sort of 4 times larger than the area outside of that circle. So what you're essentially doing in this case is doing the sampling procedure, which is, you know, throwing your rocks or, you know, coconuts into this area. And this this concept is analogous to what you would be doing in figuring out a output distribution for any model that you're doing, right? We are selecting a set of inputs to calculate a sort of distribution of outputs. And if you did this sort of many times over and over again, you would, right, eventually arrive at a fairly accurate value for pi. Okay, so I was providing some examples of distributions. And so you need to be able to choose the sort of appropriate distributions and think carefully about what sort of makes the most sense and whether you actually even sort of need a distribution. For discrete distributions, you could have something like a binomial distribution where you have some probability that's just a sort of yes or a no. You can have a Poisson distribution, which is the probability that some number of events occur over a period of time. Poisson distributions are really useful for providing distributions to sort of really infrequent events. So common examples of these are like natural disasters. So oftentimes people would use like a Poisson distribution to represent like the probability that like an earthquake would happen in any particular year, right? The probability could be really small, but generally, you know, over a period of like 100 years, you can, in some places, get a fairly accurate number of times that like a particular event would occur. Okay, so for continuous distributions, there's the sort of normal distribution, right, based off of a mean and standard deviation parameters, and this creates like a sort of 3 sigma rule, right? So within each standard deviation, some amount of the value will fall within that area. You can have a log normal distribution. So this often describes values that have to be sort of positive. So a log normal distribution ensures that you don't go below 0. A triangular distribution, as I was mentioning before, is if you know just the most likely points and the range, and then the uniform distribution. If you only know information about the sort of min and max, this is a type of distribution you can use. So going back to our original example of this decision tree for this lawsuit, I can take those same 5 variables that we were looking at in our one-way sensitivity, and let's say I just apply a couple different distributions to them. You can see kind of what they look like here. So this is like except the Texaco offer, this is a normal distribution. The Benzel counteroffer value is a triangular distribution. I made the court case winnings as a uniform distribution, looks like this. And then the Texaco counteroffer as a normal distribution. And so again, this is just kind of an arbitrary example of distributions that I kind of made up for each of these parameters. And what we can see in the output is now, instead of just saying yes or no to each of my decision nodes, I can have sort of distributions of values. Okay. So this is the typical sort of result that you would see in a Monte Carlo analysis, where your outputs are now represented as distributions instead of sort of static values. And so generally, let's just look at the first offer. So that's going to be my green and my red. You can see the sort of distribution of values based off of the sort of information that we have in our inputs. And we can see that the expected value of declining the first offer in green versus accepting the first offer in red is a lot more often higher than the red bar or the red distribution, where you would accept the first offer. So in this particular case, I think sort of making the decision to accept versus to decline is a lot easier than, say, if the distributions were overlapping quite a bit more, as we can see in the sort of second offer. And so this is the type of thing that would be a lot harder to see in the static analysis, where we just say kind of yes or no. Okay, I see a question. Are the grays overlapping decisions? So anytime the overlap is happening, that means that, okay, there are some combinations of values in the first and second, in the accept versus decline, the first offer, where in theory, the first offer could actually, accepting the first offer could actually have a higher expected value. And so if they were sort of completely separate, right, then there's no combination of values based off of our input distributions where, you know, one decision would, all combinations of values would indicate that it is always better to do one versus the other. In this case, that's not necessarily the case because they overlap. And same thing with the blue and the orange, because there's some overlap. And so, you know, one simple way of putting it is that sort of the more they overlap, the less confidence I have that one decision might be better than another. Or in a more generic example, like if they're representing like monetary values or emissions, maybe I would have more or less confidence that, again, one might be better than another. Okay, any questions about this?
So in this case, I guess the most obvious course of action would be declining the first offer,
Yes.
and then accepting the second offer, or
so okay. So I'll agree with the first one. Let's look at the second one. What, just based off of these distributions, I guess, what would you say? Which one has higher expected value, the blue or the orange?
the blue
Yeah,
by a little bit.
by a little bit. Yeah. So I think that, so blue is decline the second offer. So I think, you know, if I were a betting man, right, I would say I would decline the first offer and I would decline the second offer. But for example, the second decision is a lot closer. And so you might not necessarily, come to the same conclusion. And in fact, we have, what we're looking at is something like this. So if I were to kind of draw this, maybe I have something that looks like this, where my distributions look kind of close. So that decision might be a little bit less clear because because they're a lot closer together, but maybe I would still go with blue declining in this case.
Also, if you decline, then if I remember correctly, you need to go to court, and then, I'm thinking about the process. If you just accept, it's almost the same, like they're very close, and you don't have to go through that cumbersome process.
Yeah, but I think the whole point of this is that it should capture the sort of full range of outcomes and probabilities of those outcomes. So these distributions should kind of represent the likely things that you can see. What I will say is that yeah, so that's right. So as being pointed out in the chat, blue has the higher frequency for higher EB, which is right. What you see as the what you see if the distribution is shifted more to the right. Okay, in this case, I think the shape of the distributions makes it kind of more obvious. But okay, let me draw something instead of doing like that. Let's say it actually looks something like this. So in this case, you have the blue is still the sort of mean expected value might still be higher than my yellow distribution. So let's say the expected value is kind of the same as in the one with the sort of narrower band. However, in this case, what you can see is that the distribution of outcomes is a lot wider. And so purely going by someone who is kind of an expected value taker, rational actor, then you would still choose blue. But because there is some risk, right, that you could have a sort of lower value, you can see how that might change someone's decision because, okay, maybe I prefer the more sort of certain payout, right? And so this analysis, again, it's like a tool to give us more insight and perspective for any particular sort of outcome. And you can hopefully start to see how this might be applied not only to, say, some kind of like financial or economic analysis. Like I could do the same type of thing if I were to like measure emissions, for example. And in fact, we'll look at some nice examples of how this has been used in sort of like a policy context. Okay, yeah, I see a question, maybe compare the size of the area above a certain frequency. Okay, yes, we are getting actually to the sort of next, to the next slide. So good transition, but actually let's take a quick moment here and do a 5-minute break. So let's go till 11:06, and I'll yeah, I'll be here for any questions, and I'm gonna dig up that link for the Excel add-on right now. Okay, returning to interpreting these results. Yeah, so there was a really nice point brought up in chat about essentially comparing the size of the area above a certain frequency. So this is known as stochastic dominance is a type of thing where we can interpret these results in a certain way. So if A is better than B because A provides unambiguously high returns, what we could do is essentially for any value, for any set value of X, right, the probability of getting at least X is higher under A than B, which means essentially it's saying, you know, you could have correlated values in X where they correspond so that you could, for example, never actually get higher or lower than particular values, or the probabilities of your outcomes are aligned in such a way that your distributions may not sort of overlap. And in that case, you can sort of strictly say that one outcome is better than another. And you're still getting kind of more information at the end of the day, right? Because you have a lot more confidence in that answer. Whereas before, you know, when we said, you know, one expected value is better than the other, that may not apply under sort of all circumstances. So what does that look like? Essentially, you create cumulative probability functions. So if I were to plot this exact same plot that we just showed from before, except that now I arrange it as a CDF, you can see how those distributions look like. And when the distributions don't overlap, so the sort of clear example of that is this green and the red for accepting or declining the first offer. What ends up happening is that then I can say, no, it's always the case that that declining the first offer has a higher sort of EV than the other. Now, if your CDFs ever sort of intersect, in this case, it's not the best example of it, but you can see here, sort of right at the top, there's some small probability in which the EVs will sort of meet and cross, then they are not strictly stochastic, they don't have stochastic dominance over another sort of option. So sometimes you may see these curves overtaking one another, in which case you don't have a clear example of stochastic dominance. And again, doing this is a nice way of just demonstrating essentially that one outcome is always going to be sort of higher or lower than another outcome, even across the sort of ranges of sampling that you do. Okay, the last one that we'll do is we'll apply distributions in the insurance example as well. So in this case, we'll have a triangular distribution and then some sort of normal or log normal distributions for our probability of accident and then the cost of the accidents. Same type of thing here. I can just, they're not sort of comparative inputs, but I can see a just sort of distribution of what my output values might look like. So how might the shape of the distributions in a Monte Carlo output inform an answer? So considering the range of possible values and density of those values, so you can see the amount that the insurance would charge can vary over sort of this distribution, and the amount of profit that they would have could vary over this distribution based off of our input parameters. Okay. One little sort of nuance about Monte Carlo is that you could have inputs that are correlated. In other words, if my X going into the model, if you have like X1, X2, X3 going into the model, but then X1 and X2 are correlated, you can still do Monte Carlo with correlated draws. In this case, you need to slightly modify the procedure since the draws are not independent. What you can do is draw randomly from your first distribution, and then you could then do your correlated distribution draw on whatever variable is correlated to the first one, given the information about the first draw. So it just makes the sampling procedure slightly more complex, but you're still able to do this sort of analysis technique. Oh yeah, I guess one thing I didn't mention is that if I go back a couple slides, if I were to look at this particular example, you can see that my outputs are kind of these smoother shapes and of distributions. So there's this question of like, oh, how many draws do I need from my input distribution in order to get at a correct answer? And so that is, there's not really a good sort of generalizable way of giving, the number of samples that you need to do or the number of draws, because it's so context dependent to your specific model. It can, like the higher the number of variables that you're drawing from means that you have to look at larger numbers of combinations. And then the way that it's sort of modified through your algorithm can determine whether or not you need sort of more or less. And then even the sort of range of values that you're looking at can have some play on the number of draws that you need. My general rule of thumb is to, start small and increase the number of samples that you need until you reach a point where your output distributions look sort of relatively smooth. So something like this. In the case where you have correlated draws, oftentimes you're going to need a sort of larger sampling size than in independent distributions. And that's because the way you can think of it is like you have distributions that rely on other distributions. And so to get an accurate picture of your correlated distributions, you need to have quite a lot of sort of draws from your, your first distribution. So Monte Carlo can be integrated into tons and tons of different techniques, optimization, decision trees, regressions, and choice modeling. And so this is a super handy technique anytime you are aware of uncertainty. You can almost always apply this sort of analysis to your model to get a better sense of uncertain outcomes. You may have also heard of a technique called bootstrapping. This is very similar to Monte Carlo. They're both simulations that are based on repetitive sampling. The sort of distinction between the two is that in a Monte Carlo, you are drawing from distributions where you know information about the parameters. So this might be something like, oh, I know the mean and standard deviation of my set of inputs. And so I can then create the distributions myself. Bootstrapping, instead of doing that, is that you have some kind of population or sort of large data set that provides the values for the distribution. And instead of inventing the distribution, I simply select from directly sampling from that initial data set. And you sample from it many times, and that allows you to have a distribution of input values. So they're, I would say, very close to being kind of the same thing. It's just that one depends on the parameters of the distribution, one depends on having sort of data that define the distribution. Okay, any questions about that? All right, so what I'm going to show, I'm just going to show one last example for today of a real world application of this. And this is actually from sort of a paper that's we had published a couple years ago. So real world example, bootstrapping technique to get at the sort of charging profile of electric vehicles, right? It's one thing to say, oh, okay, if I want to, for example, if I want to know how much energy a electric vehicle is charging in a given time, you could do sort of like some kind of average based off of all of this information, or I can kind of construct this distribution using bootstrapping techniques. And so, does the vehicle charge today? Yes or no? And we have some information about how much it needs to charge and how often it charges, right? And so that would be something like this chart here is like on Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. What's the sort of relative probability that it's charging on like a level 1, level 2 DC fast. And then for short range all the way to long range. So we have sort of different distributions of whether or not a vehicle will charge on a given day. What rate does the vehicle charge? Does it charge slow or fast? And so we have another set of distributions telling us that. What time of the day does the vehicle charge? I have some distributions here over a period of say 24 hours. You know, are they more or less likely to charge at certain times, depending on if it's a slow charger or a fast charger? And then when it does charge, how much energy does it actually use? And then I have sort of these distributions. So all of these are, right, essentially my X input variables, and I have distributions from which I can sample from. So in exactly the same way as what we do in the Monte Carlo, I can pick a single value from all of these, go through a set of calculations to see how much energy, and then I can do that sort of again and again. And ultimately, what you end up with is, oh, okay, and of course this one doesn't have my uncertainty bands for some reason. Okay, but imagine that there are some kind of uncertainty bands around each of these lines. You can have kind of the distribution of the charging load shapes over the course of a day for sort of different types of vehicles. Yeah, so this is kind of a real world example of an application of like a bootstrapping or a Monte Carlo technique. Again, once we start getting at the sort of end of the course, when we get into policies, specific policies, we'll be able to see exact examples where this type of analysis has actually helped informed decision makers about how to construct certain policies. Okay, and that's actually all I have for today. So we're going to end extra early today. Oh yeah, sorry, question. Sorry, so what does XFC stand for? That's extreme fast charging. This particular paper that we were doing was a paper about looking at how extreme fast charging might get used in the future and what kind of like energy and emissions implications that would have. So XFC stands for extreme fast charging, and that's like thinking about chargers at like 350 plus kilowatts. Yeah, I see another question.
Yeah, so in this example, we are using the bootstrapping technique instead of
Yes.
Monte Carlo.
Yes.
So the first question here, the base data is the initial data where we have taken the population, or is it the number of electric vehicles which are in use? Like, what is the base data here exactly?
You're talking about for each of these distributions?
Yes, yes.
Yeah. So let's see. So I'll give an example. So this this distribution in the bottom center about when does the vehicle charge, this distribution we took from a couple different data sources that basically tracked the time at which an electric vehicle would sort of arrive and plug in their car. And so you do this many millions of times and you have like some idea of, that's a pretty accurate idea actually of what time of day people are plugging in their car. And then there are other data sources, like for this one, this is from a large scale survey with say, on the order of 50,000 plus respondents, where we would say, okay, in the last week, what days did you plug in your car? And then we can, build off of the fact that there's, we have so many respondents that we have some sense of how many, on a particular day, like how, which day they would be sort of charging in their car. Because, one of the things that we were trying to get at with this analysis is that like in a lot of common analyses, people use these like travel diaries and they say, okay, so this guy drives this amount in a day, gets home, plugs in the car, and then charges that amount. But what we know from kind of sort of general knowledge in doing this, working in this area, is that like people don't charge every day. Owning an electric vehicle, you might not drive that much, or you don't want to bother sort of plugging in the car, and so that changes the profiles because on some days, I plug in the car and then I use a lot. Maybe I have to charge a lot more because I hadn't charged in the last like 3 or 4 days. And so we were trying to capture that here.
Okay, so sorry, another follow-up question. So
Yeah.
here we are taking into account the public charging infrastructure, and also, but there are so many people who are charging at home. So do we have an uncertainty there? Like if they're not reporting that they're charging at home.
So these two, so this one on the right side is public charging. These two are home charging at lower levels. And this data was from an Idaho National Lab study that basically tracked a bunch of people who were charging at home, and then we were able to get like time of the day that people would be charging at home. Yeah, couple questions in chat. So do I have example code for the Pennzoil plots that I can share? Yes, I will post those into Canvas. So I'll make sure everyone has access to that. And I code mainly in R. So if you're familiar with that, then you can build off of what I was doing. If not, you can always use the sort of trial version that I linked using the Excel add-on. Okay, I see another question. Is it necessary to distinguish across different models and makes? Yeah, that's a good question. So there's this idea that like, okay, if I were driving, you know, like a first generation Leaf where I only have 80 miles, the pattern in which I would charge my vehicle might look really different than if I were driving like a 300-mile Tesla. And so we tried to control for that in this particular case by separating into broader categories where you have sort of like a short range and long range battery electric vehicle, and then short range and long range plug-in hybrids. So we didn't distinguish by specific models and makes, but we did try and break out differences in broader sort of categories of electric vehicles. Okay, and then yeah, so that's it for today's lecture.